Okay, we're going to do the second problem on this slide, the whiteboard problems 1.8.4. So we have a geosynchronous satellite is one that stays above the same point on the Earth. So as the Earth rotates, it's rotating at the same angular speed, right? So it stays above the same location. So determine the height above the Earth's surface such that such a satellite must orbit and the satellite speed. Okay, so let's go over to our page and write down. So maybe first we'll just draw a picture, right? So I try to kind of visualize this. Imagine that you're looking down at the Earth from the North Pole, and let's say the Earth is rotating around this way. So it's some pretty far distance away is a satellite, which I'm going to draw as like a box with maybe little wings on it. Okay, and this is going around in a circular motion with the same period, right, of 24-hour period. So that's actually one of the things that we are given, that the period is 24 hours. And if we multiply that by 3,600 seconds per hour, that's equal to 8,640 seconds. That's good to know. What else do we know? We know just some constants that you can look up here. So the radius of the Earth would be good to have. That's 6.378 times 10 to the 6 meters. It is a gravitational problem again, so we'll put down that we know the gravitational constant, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. And then also we will need to know the mass of the Earth. That's 5.97 times 10 to the 24 kilograms. Okay. All right, so let's think about this free body diagram of the satellite. So what we want to find, right, is first we want to find the radius of the orbit, and then also the speed. And so this is my distance r. Okay. All right, so this is a circular motion problem where gravity is providing the centripetal force. So if we do a free body diagram for the satellite, here's our satellite, taking the same kind of view, there's a force of gravity. Maybe we'll say F big G, right? Because it's not just like the acceleration on the Earth. And that's it, actually. And so my direction is going to be, that's my radial direction, and that will be, this actually is my tangent direction if I'm doing a top-down view. But it doesn't matter, we're just going to be working in the radial direction. So we have the sum of the forces, right, equals MAR, or we'll just do the general one first. Sum of the forces in all directions will produce an acceleration. We know the only force actually is in the radial direction, so we can rewrite this as the sum of the forces in the radial direction is MAR. And we know from centripetal acceleration, right, if something's moving in a circle, its acceleration is v squared over r. And then from the free body diagram, we know the force is provided by gravity. So it's G, mass of the Earth, times the mass of the satellite. I'm just going to call that little m, over r squared equals the mass of the satellite, again, little m times v squared over r. So my little m goes away, doesn't depend on the mass of the satellite. And the first thing we want to find is r. So we have to remember, we don't know v either, right? Because that's the second thing we have to find. So remember, for circular motion, we have this relationship we want to keep in our back pocket, right? And there's a tool that our velocity or speed, right, is a distance of travel. So that's going to go around 1 circumference, 2 pi r, divided by the period. So the period, by definition, is how long does it take to go around once. Okay, so that always an expression we can use for our speed. Okay, so then if we rewrite that, also before we go on, we have 1 over r on both sides. So if I cancel that out, I can reduce that by 1. Or another way we could say that was multiply both sides by r. Right, okay, so we get GME over r equals v squared. Okay, and we're going to say that's 2 pi r over the period squared. Okay, so that equals 4 pi squared, r squared over the period squared. So the first thing I want to do is find r, right? So I'm going to get all the r's on the same side. I'm going to multiply both sides by r, and I'm going to move this stuff over to the other side. So g m e, I'll get a period squared on top and divide by 4 pi squared. And then I'll move my r over the other side and I get r cubed. So this basic relationship, right, you have period squared is proportional to the radius cubed. This is known as one of Kepler's laws. I believe it's I can't remember, second or third law. Period squared is proportional to the distance cubed. He actually found this out for this relationship for the planets that are orbiting the sun, but same kind of problem, right, where you're orbiting a central object. Okay, so let's go ahead and plug in now, and we can solve for the radius. So our radius equals the cubed root of GME, our period squared, divided by 4 pi squared. And if we plug in our values here, we have 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared, times the mass of the Earth, which we wrote up there, 5.97 times 10 to the 24 kilograms. We'll do our period, 8.64 times 10 to the, oh, I did it again, you guys, 10 to the 4. I ran out of room. Seconds squared, and then we divide by 4 pi squared. Okay, so if we plug in those values, we get that r equals 4.22 times 10 to the 7 meters. If you divide that actually by the radius of the Earth, this is actually equal to 6.62 times the radius of the Earth. So just to kind of visualize that, I probably didn't draw it far enough away, right? But if this is 1, 2, 3, 4, 5, 6. So if we were doing more of a scale model, that would kind of be the distance of these geosynchronous satellites from the Earth. So they're pretty far out there. Okay, so then the last part is just calculate the velocity. So we need 2 pi r divided by the period. So 2 pi, 4.22 times 10 to the 7 meters. And our period is 86400 seconds. And we get that these things are booking around at 3072 meters per second. We'll put that in scientific notation, 3.07 and 10 to the 3 meters per second. That's pretty darn fast.